Okay.
Okay, so good morning for everyone. So today I'm going to continue this discussion about the problem of elimination of nilpotent points for vector fields in dimension 3. But before discussing the result, I would like to comment on some new example, which I find quite interesting, which shows us let's say this procedure has a lot of potential applications, even if you're only interested in dimension 2 problems. Yeah, so I recall to you that last time I commented on this example of vector fields in dimension 3, which don't have C-infinite center manifolds. So this is let's say some new phenomena that doesn't show up in dimension 2. Well, there is a general result which shows that center manifolds are always CK for all K, finite K, right? So in fact, the phenomena here is that when you reduce the neighborhood of the origin, you increase more and more the degree of differentiability that you can attain. But in some sense, it's always finite as long as you stay in some neighborhood of 0. Okay, so I'm not going to comment on this example anymore, but so I'd like to tell you about some new, let's say, application of this resolution of singularities, which I found quite interesting, and it indeed has a lot of people which are working on this right now, which is the so-called geometric singular perturbation theory. So I'm going to illustrate this by the case of the so-called van der Waals equation. So what's the phenomena? You consider this family of planar vector fields. So it depends on X and Y variables, but the expression changes as you change these two parameters, epsilon and A, right? So there's a 2-parameter family of planar vector fields, right? So it shows up, let's say it's a very classical model which appears, for instance, in the modeling of the transistor, which is given by van der Waals. And well, the novelty here is the appearance of this epsilon in front of the second equation, which has the following effect. So on the left-hand side, I've drawn let's say the phase portrait for epsilon equals to 0. So for epsilon equals to 0, the second equation vanishes completely. So you have this line of singularities, which is a cubic, which corresponds to the equation y equals to x squared over 2 plus x to the 3 over 3, right? So this is this cubic here, and outside, so the cubic is completely formed by equilibrium points or singular points of the vector field, and outside you have this horizontal foliation, which is given simply by d over dx, right? So it's oriented on this way. So the foliation, let's say you go to the right when you are below the cubic, because d over dx is negative, and you go to the left when you are above the cubic, because y minus the equation of the cubic is positive, right? So the interesting thing is that when you perturb the situation by making epsilon different from 0, then this equilibrium curve disappears. And in fact, there is only one singular point which remains, which is situated at, let's say you just take now the second equation and you put x equals to a, and then you represent the third equation. So there is the singular point which lies on the cubic, right? And well, it has been observed a long time ago that there is this, in general, there's a limit cycle. So it's an isolated periodic orbit which persists by this perturbation of epsilon, or more precisely, it appears by this perturbation. And then what is interesting is that the shape of this limit cycle, it depends in a very delicate fashion on the parameter A, right? So there is 2 parameters, epsilon and A. And you can show that when you make epsilon goes to 0, depending on the choice of A, this limit cycle, it converges to different forms, right? So here I've drawn 3 different forms. And in fact, all of these forms, let's say the limit form of the limit cycle, in some sense, so it more technically, it's called the limit periodic set. It can decide, let's say it's everything is decided in a very, very small exponentially flat tongue. So this is the region of the form A equals to some, let's say, some central curve C0 of epsilon plus some exponentially flat term here, right? So it's a very, very subtle phenomena, which is, in fact, numerically is quite difficult to detect. Okay, so yeah, I make a different drawing here where you see all possible shapes of the limit cycle when epsilon goes to 0. Okay, so depending on the value of A. So these are the so-called canard limit cycles. So there is a very nice paper of Dumortier and Roussari where they study this phenomena using the singularization of in dimension 3, or more precisely in dimension 4, because you have 2 parameters. So what do you do here? So let's suppose that A equals to 0, just to simplify the computations. So you have this family, which I've written before, with A equals to 0 now. And I want to desingularize this family. Why? Because let me just go back. In this leftmost drawing here, every point which appears on the cubic, every equilibrium point which appears on the cubic is an elementary point, because you have a non-zero eigenvalue in the horizontal direction, except for these 2 red colored points here, which are nilpotent, right? So the idea, as you can see, is that there is some interesting phenomenon which appears in the vicinity of these red points. And it's precise, the idea is precisely to desingularize this point by a weighted blow-up. Okay. So I'm going to explain how to desingularize the point at the origin, let's say the rightmost tangency point. So, okay, so again, you force the expression, the appearance of this logarithmic base here. And now you have to recall that you have an additional structure on the ambient space, which is the so-called family structure, which says simply that your vector field is tangent to the fibration given by epsilon equals to constant, right? Because epsilon is just a parameter here. Okay, so now what you do is that in order to choose the weights, you have to make well, it's the same thing as drawing the Newton polyhedron in this case, but you can also look at this choice of weight as a sort of equilibrium equations, right? So you look at this first equation here, and you say that the weight of minus the weight of x plus the weight of y should be equal to the weight of x, right? So you want to equilibrate these first 2 terms which appear here. I cannot. The third term you cannot equilibrate. You cannot put in equilibrium, and at the same time, the choice of the weight that you're going to choose for making an equilibrium between these 2 terms should also be the weight of this rightmost term which appears here, right? So the second equilibrium equation is this one, right? So, okay, so this is one of the choice, let's say, which don't have any common factor. Weight of x equals to 1 is a linear system, right? So weight of y equals to 2 and weight of epsilon equals to 2 also. And now when I'm going to make the blow up with this weight 1, 2, and 2, and now you have to think of this as the following thing. Now you have an object in 3 dimensions, which is tangent to the fibration epsilon equals to 0, right? And now I'm going to replace the point, which is at the origin, by a sphere, right? Because let's talk about the real blow up. So once you replace the point on the origin by a sphere, okay, you obtain this rightmost drawing here. And now what happens is that this cubic, the singular cubic, which let's say which appeared in the before blowing up, now will accumulate in the boundary of this in the boundary of this in the intersection of this sphere with the fiber epsilon equals to 0. Okay, so this is the curve gamma that I've noted here. Okay, so well, I'm not going to enter in this computation, but I think it's perhaps a nice exercise to make them. So we use these two charts. So there is a chart which is, let's just go back here. There is a chart which is in the direction of epsilon. So the direction which is goes outside the screen, right? And one I compute also in the direction which is vertical, the y direction, which is the direction which is goes vertically to the top. Okay, so in the epsilon direction, you get what people call usually the rescaling. So this is a classical transformation that you do in the singular perturbation, in the classical singular perturbation theory, which is called so-called the rescaling. So by this rescaling of variables, which is simply the blow up computed in the epsilon chart, you see that there is a sort of miracle which happens because recall that there was an epsilon multiplying the second component here, the component on x d over dx, but it disappears. It disappears precisely because after blowing up, you divide out everything by the highest power of epsilon that you can factor out. So of course, and you can say that the fibration in this case remains the same one given by the pullback of this equation of this differential form by epsilon. So this gives you the same equation. But in fact, this does not capture all the phenomena because you have to compute what happens in the other charts, right? So let's just look at what happens in the second chart. There's a third chart also, but let's just give the vertical chart. So in this chart, you have these equations and the blow up, well, given by, I'm not making the details, but the interesting thing here is that the fibration now is no longer given by smooth fibers, because when you pull back this form d epsilon by replacing epsilon by y square epsilon, then you have this singular differential form here, which corresponds to, let's say, I'm going to make the drawing only on the epsilon chart. So you have the fiber given by y square epsilon equals to 0, which is the union of these two planes, right? So the plane x equals to 0 and the divisor, sorry, the plane given by epsilon equals to 0 and the plane given by y equals to 0, which is the divisor in this case. Okay. And now, well, in fact, these two bold lines here are exactly the, sorry, I'm going to go back. There are exactly the strict transform of these two pieces of the cubic, which appears as straight lines on the epsilon chart, on the y chart, sorry. Yes, because with this blowing up, you make these two branches becomes straight lines. And then there is a new dynamics which appears inside the sphere, right? So this is a new thing, and this is precisely the dynamics which is described by the rescaling chart. Okay, which, as you said, there is no line of singularities here because the epsilon has disappeared. Okay. So in fact, what you do is that you compute the, let's say now I have a three-dimensional vector field here, as you can see by this image, but it respects some additional structure which is given by the fibration y square epsilon equals to constant, right? So the 2 points now, so this is but in our sense, this is the singularization because all points now are elementary, including the red colored points that I've drawn here, because now they have also a non-zero eigenvalue in the horizontal direction. Because in some sense, by blowing up, you have eliminated this tangency between the cubic and the horizontal foliation given by d over dx equals to 1. Okay. So now there is a Roussarian de Mortier has interpreted. So there is a very classical tool that you use in the singular perturbation theory, which is the so-called matching of asymptotic expansions, right? So you have what the people do is the following. So when you are in the regular part, the part which there is no nipotency, you have a very well-behaved singular asymptotic expansion. And then there is this rescaling map where you have some new asymptotic expansion. And what people do is that they say, well, you have to match these two asymptotic expansions by using the rescaling map. Okay. What's the let's say the geometric interpretation of this? It's the following one. So you have these two red points, and these points, in fact, they are, as I said, they are elementary points, but this point, they have one non-zero eigenvalue in the horizontal direction, but in the two, in the y direction and the epsilon direction, you have zero eigenvalue as an eigenvalue. So by this, we mean that there is, as before, there is a center manifold through these points. Okay. And this center manifold, in fact, there is a whole bunch of center manifolds because what you do is that you can obtain a whole family of center manifolds by saturating some curves which appear on the, let's say, when you look at things outside the section divisor. So here I've drawn one of these center manifolds, but let's say by this I have chosen one of the heights of on the cubic. But if you go to another height here, you get another center manifold, which is if you look at them on the red point, they are exponentially, they have an exponentially flat contact between them. Okay, so all these center manifolds, they have a flat contact between them on the red points. And this is precisely the reason why this phenomena happens in an exponential flat tongue that I've drawn in a moment ago. So you have this family of center manifolds, and now how do you see the limit cycles, right? So now you recall that you have the fibration. So if you look at a nearby fibration, which is given by y squared times epsilon positive but small, right? What you see is that the intersection of this fibration with the center manifold gives you this curve, right? And this is one of the limit cycles. So in fact, the idea is that by using blow up, you can reduce the study of this canard limit cycles to a problem of the study of, let's say, globally defined center manifolds for such kind of configuration. Yeah. So, well, this is I think there are a lot of people which is working on this subject right now, and now it's called the geometric singular perturbation theory. Okay. Yeah. So let me just relate this to a problem which, for me, it's quite interesting because, in some sense, it's even more irritating than the Hilbert 16 problem. You see that here. In fact, we have shown another sort of mechanism for the appearance of limit cycles, which is not the usual mechanism that we see when you study, for instance, Dulac's problem, where there is.
Excuse me,
yeah.
Daniel.
Yes.
Can you go back to the previous? Yeah. In this picture, it seems that the center manifold, the local center manifold at one point, at one red point, do not match with the other. It seems that they are not gluing. It's actually
yes.
in.
Yeah. That's true. Yeah. In fact, how do you construct this center manifolds? You take one curve. I don't know if you can see the pointer of my mouse here, but you take one transversal curve which lies on some height here, and then you saturate to the left by the positive flow and to the right by the negative flow. Yeah. Right. Or or perhaps better, even better. Here you take a point on the exceptional divisor, a small straight line, which let's say it's transverse, and then you saturate. But when you saturate by the flow positively and negatively, you end up above here with two curves which perhaps do not match. Right. So this is so the idea is that when they do not match, you don't have a closed curve.
That was the question. That was the question, because the distance
So sorry. So then this is the role of the parameter A, because the parameter A, in fact, it has the role of moving these curves in such a way that they're going to intersect transversely by changing the value of A. And this is the way to create the limit cycles. So in fact, this is why by changing, sorry, I'm going to go back, by changing the value of A, the matching between the center manifolds will happen in different heights. And this is the canard phenomenon.
Okay, thank you. Yeah, I was interpreted that there were always limit cycle, but it's not true. It depends on the.
No, there is always one, but its shape. I mean, the height where these center manifolds intersect will depend on the parameter A. Okay, okay. But yes, that's here I've drawn a case where they match, and then you have this closed curve. Okay. So yes, yeah, so I was talking about this. You're talking about this Hilbert's problem. So there is the Hilbert 16 problem, which the problem, of course, asking about the uniform bound for the number of limit cycles for vector field for polynomial vector fields of a given degree, right? So there is an easier problem, which is also which is still very difficult. Which is the so-called Dulac problems, where you just fix one polynomial vector field and you ask about the finite cyclicity. Okay. Well, so if you fix one polynomial vector field of a given degree, of course, you have a whole bunch of different configurations which are possible. And then you have to, first of all, classify these configurations, and already the finite the finiteness of the number of limit cycles for a fixed polynomial vector field is a quite difficult problem. And so Ismail, in his list of problems for the 21st century, he simplified this problem and asked the following question. So you have a particular case of the family of polynomial vector fields of a given degree, which is the so-called linear family, linear family. Okay. So it comes from this second order differential equation, right? So it's perhaps the simplest second order differential equation that you can imagine, which is nonlinear. You just put a polynomial here. So it's a polynomial in T here. Sorry, I've made a mistake here. It's a polynomial in X. It's right. Okay. And you can write the differential equation associated to this as a system, in planar system of this form: y minus p of x d over dx minus x d over dy, where a capital P is a primitive of a small p, which vanishes on 0, right? So the problem asks, in the case where capital P is a polynomial of degree 2n minus 1, okay, can you give an explicit bound for the number of limit cycles of this particular family? Depending on n, of course, because here there's the only parameter now is just n. Well, in this case, if you take an individual element of this family, things are very simple. Why? Because in fact, this is a sort of phase portrait in the case where you fix one polynomial vector field. So you have this, so this is the curve given by y equals to p, and then the vector field, it turns around like this, And for a radius sufficiently large, you can show by this condition here that everything goes inside. Okay, so there is you can say that the infinity is a repelling point for this dynamics. So everything happens in a finite region, and moreover, there is a single fixed singularity here, right? There are no other singularities except this one. So in fact, so you can prove that a solution curve in this region, it has to turn around, right, at this singular point. And in fact, there is a globally defined first return map, which I denoted by this, which, well, in the, let's say, in the interesting cases, it's globally analytic. Okay, so globally, I mean, by in a finite region of the plane. So even at the origin, right? It can extend this first return map to the origin as an analytic map. Okay, so in this case, the finiteness of the number of limit cycles corresponds to the finiteness of the number of fixed points for isolated fixed points for t. And this, of course, it's a trivial issue because t is analytic, right? So for each polynomial p, the Poincare reference is analytic. So in this case, let's say that the analog of the Dulac map is completely trivial because it's finite due to the analytic problem. But now the question remains as what happens when you consider all polynomials of a given degree. In this sense, you have to look in all, let's say, to the whole space of parameters, and in some sense, when you compactify the space of the parameters, which are nothing else than the coefficients of this polynomial p, what you find at the boundary by taking the parameters greater and greater are precisely the singular perturbation that I've drawn to you here. Okay, so in fact, these singular perturbations, they appear at the boundary of the Leonard family. So with this, it's possible to give. There was an old conjecture, let's say, quite old conjecture, which said that the number of limit cycles should be bounded by n in this case. But we were able to give a counterexample by this, precisely by studying the boundary and showing that when you look in the singular perturbation setting, you can have more than n. Starting from n equals to 3, there is a counterexample to this conjecture. But as far as I know, this conjecture is so it's true for n equals to 1. For let's say for capital P of degree up to 3, it's true. But as far as I know, it's open already for n equals to 1. Yes. For polynomials of degree 5, it's for n equals to 2. Yes. For n equals to 2, it's open, as far as I know. And this is, let's say, it's quite surprising because you see, you have a very simple equation, and the phase portrait, it's quite easy to understand. Okay, do you have any questions about this? No. Okay, so I'm going to now to enter on the subject of this of today's course. It's how to define this resolution of singularities for vector fields in dimension 3. Right, so here I've made a drawing of a polyhedron in dimension 3. Now we are going to see how to choose this so-called main phase, and then to define a local resolution strategy. Okay, so now the setting is the following. We have M, a three-dimensional real analytic manifold with corners. So E for us, which is the, let's say, is the normal crossing divisor in our case, will consist of the boundary of M. So the boundary of M now is It's two-dimensional, and it's given either by a plane, by two intersecting planes, or by three intersecting planes in normal crossing position. And now F is a singular foliation by curves, which is tangent to E, to the boundary, and such that, so this is an important condition, the locus of the nilpotent points is of codimension greater or equal than 2. Okay, so it means that recall that this hypothesis in the case of two-dimensional foliations allowed us to consider only isolated points. But now it's inevitable to have curves of singularities. So we have curves of nilpotent singularities, which eventually in our resolution algorithm should be taken as a center of blowing up at some point. Okay, so now the goal today is to explain to you how to define this invariant, the invariant that will decrease after each blowing up step. And you're going to see that it's a little bit subtle because due to the presence of points on the polyhedron which have negative indices. Okay. So to explain the invariant, I'm going to place myself in the following typical situation, because in some sense this is the situation that you can attain by some preparatory steps, and this is where the main difficulties lie on. I'm going to explain later on how to end up in this typical situation. Okay, so you have a germ. Let's say M now is a germ of a manifold, a neighborhood of the origin in R3. And let's suppose that the origin is a nilpotent point. And moreover, this is an important condition, is that the divisor is either given by x equals to 0 or by x times y equals to 0. So in particular, I'm not going to treat the case where you have three components of the boundary or divisor intersecting at a point which is in the nilpotent locus. And the third condition, I'm going to explain to you how to obtain this condition, is that the vertical axis, so the axis which is given by the intersection of the two, let's say the two components of the divisor, is not entirely contained in the nilpotent locus. Okay, we're going to see why this condition shows up a little bit later.
So sorry, Daniel. So,
yes.
So this condition you are imposing this situation where the nilpotent point is not in the intersection of three planes.
Yes.
Is it something? I mean, it's a situation that you can reach after, in general, after some convenient transformations, or
yes. Yes. Okay. So if you start with a situation where your manifold M has no boundary, by which I mean E is empty, then I can prove that you are never going to attain a case where E has three components on a nilpotent point. Okay.
Okay.
So, but if you start a situation where the divisor exists, then you can, in some sense, eliminate this bad situation by some preparatory steps also.
Okay.
Let's say this is why I call this a typical situation, because everything which is not in this situation can be obtained. Let's say we can eliminate by some easy preparatory steps.
Okay.
So the core of the problem lies in this case here. Okay.
Okay. Thank you.
So you have this nilpotent polyhedron, which is associated to F, and of course, which depends on the choice of local coordinates. So I'm going to comment this a little bit later. So let's suppose that we fix some coordinates, and then based on these coordinates which are fixed, I'm going to define the invariant. So first of all, there is the higher vertex of the polygon is the minimal vertex with respect to the lexicographical order in Z3. Okay, so here we already see that there is the order of the coordinates will play an important role here. So you take the vertex of the polygon, which is the minimal one with respect to the lexicographical order in Z3. I'm going to give an example in a moment. So by the above assumptions, this vertex H has necessarily this form. So its first component is 0. Why? Because the foliation is tangent to the divisor x equals to 0. I'm supposing also always the presence of one of the divisors in this typical situation. But on the other side, there is the locus of the nilpotent points is of codimension greater or equal than 2. So I don't know if you recall, but in this, when you combine these two hypotheses, this one with this one, you end up by concluding that the first component of this higher vertex H should be 0. Okay, it's greater or equal than 0 because the divisor is invariant, but it's not strictly greater than 0 because otherwise the divisor should be contained in the nilpotent locus. Okay. So there is these two other entries in the higher vertex, which eventually can be negative, right? We call that the Newton polyhedron of a vector field can have negative vertices, but they are greater or equal than -1. Yeah, so this explanation for what I just said. Okay, so now I'm going the picture here represents the intersection of the polyhedron n with the plane given by V1 equals to 0. So you intersect the polyhedron with the plane given by first coordinate equals to 0. And now this is the H. So the H is the higher vertex with respect to lexicographical order. So it's situated in one of these three different possible positions, right? So let's say either, so now I consider the two coordinates H2 and H3 of this vertex H. And now there's an important separation between the first two situations and the last one. Yeah, so of course, sorry, I forgot to say this. So why H is in this one of these two positions? Because if H is more to the right than what I represented here, then the vertical axis, the vertical z-axis given by x equals to y equals to 0 should be contained in the nilpotent locus. Okay, so now to guarantee that H is in one of these three positions here, I'm using this hypothesis, which I said that it's a hypothesis that it's going to appear in the typical situation. Okay. So the first two situations will be called the regular situations, and the third one will be called a nilpotent configuration. So regular configuration and nilpotent configuration. Now, so again, this is we're going to see that there is several situations where, in some sense, you have to split into different reasonings depending on the configuration of the polyhedron. So in the regular configuration, I'm going to define now what we call the main vertex of the polyhedron. Okay, so the main vertex is some sense the vertex which will control the whole procedure. Recall that in the case of dimension 2, you also had this main vertex which showed up, but now I have to separate the regular case to the nilpotent case. So in the regular case, which are the two first ones here, the main vertex is simple equals to H. Okay, and in the nilpotent configuration, so what's the nilpotent configuration? The nilpotent configuration is the one in which the intersection of the polyhedron with the plane given by first coordinate equals to 0 has an edge which is positioned like the one that I've illustrated here in the rightmost drawing. Okay, so in this case, well, if you recall the example of the nilpotent, the cuspidal point, which is an nilpotent singularity, it's a sort of a generalization, a particular case of this configuration that I've just shown here. So this is why I call this an nilpotent configuration. So in this nilpotent configuration, the main vertex is not H, but is this N, which appears here. Okay. Well, again, we have to treat, since we are going to treat all possible cases, we have to treat these three configurations, but most of the time, the first two of them will appear in some sense. The third one is quite atypical, but it shows up, of course. Okay, so you have defined the main vertex, and now there is an important construction, which is the following one. You take the main vertex, M, and now you are going to intersect the polyhedron with a plane which is at height M3 minus 1/2. Okay, so M3 is the third coordinate of M, and now we intersect with the polyhedron with a plane which is at height M3 minus 1/2. So when you make this intersection, of course, since everything is convex, you get a convex, let's say a convex set on this plane, and this is what I call the derived polygon n prime. Okay. So now, of course.
So sorry again, Daniel.
Yes.
So this 1/2 here, when in this definition, is important. Could
you have
taken?
Yes, because in fact, I'm going to show you an example in a moment. There's a classical construction of Hironaka, which is called the characteristic polygon, which is something which he has introduced to prove the resolution of singularities in surfaces, in excellent surfaces. And in his construction, he takes one, M3 minus 1, and not 1/2.
Okay.
Now I'm going to show that it's not the same thing, precisely because in the case of polyhedrons for vector fields, you can have negative components. So it's necessary to take 1/2 here. I'm going to show an example in a moment.
I mean, 1/3 could not have worked, for example.
Also, so 1/3 would work also, but not
okay.
one.
Okay, I see.
It's sufficient, any height, let's say rational displacement, which is rational, with strictly more than one here.
Okay.
Because I recall that the vertices, let's say the polygon n is defined by integer points, right? So,
sure.
Okay, so now I have this m prime, which is the minimal vertex of the derived polygon n prime, again with respect to the lexicographical order, right? So now we have this polygon which is drawn in the plane at height m3 minus 1, and now I take the m prime as we have done in the two-dimensional cases, in the two-dimensional case. Yeah, so, and there is this displacement vector, which is simply the vector m prime minus m. Okay, so yes, with it will play an important role in a moment. So there is this delta, which is delta 1, delta 2, with our rational numbers in such a way that delta 1, delta 2 minus 1 over 1/2 is the vector m prime minus m. So it's the vector which links the m to m prime. Okay, so of course, one important question is why you have this intersection here, because it could happen that the polyhedron is so high that you don't have any, so that n prime should be empty, right? But this cannot hold. This cannot happen because, at least in the case where the main vertex has a height greater or equal than 3, the derived polygon cannot be empty. Why? Because if the intersection, let's say the n prime is empty, it should mean that the whole polyhedron is situated above the plane. So in the, let's say in the half region given by V on R3, such that V3 is greater or equal than 1. Okay, so this is the only possibility when to have a derived polygon which is empty. But if this holds, then it implies that the plane Z equals to 0 is contained in a nilpotent locus. Okay, because of the definition, you see that if you have such a configuration for your polyhedron, it means that all monomials which appear on the Taylor expansion of a local generator of the foliation should have a Z square or something like this in its expansion, and this is equivalent to say that all points are in the nilpotent locus. But this contradicts our hypothesis that the nilpotent locus don't have components of codimension 1. Okay. Okay, so this is just to see. Sorry, yeah.
Excuse me, Daniel. M, it's N in another.
Sorry. Yeah, sorry.
Yes.
I mixed up a little bit the notation. Yes. So N. So
yeah. because I was.
This is
I was hesitating if it was.
Yes. Yeah. So N. I think I've written it somewhere. Well, so N is the Newton polygon, and N prime is the derived one. Okay.
No, yeah, but the little m and little n.
Little m is the vertex. It's the main vertex. It's the one. That
the main vertex. Okay, sorry. Sometimes it's h and sometimes it's n.
No. Okay, so h. So there's two different. So at the start we have this h, which is the higher vertex.
Yeah. Okay. I'm sorry. Yeah.
So
it was written there.
Yes. In the generic case, m is equal to h, but there is this special, a little bit annoying case where you have to take this second one here. It's
okay.
Okay. But most of the time, you can think of it. Yeah. So there's this derived polygon, n prime, which I just showed you that it cannot be empty if in the condition that we are considering. And now I'm going to answer the question of Jean-Philippe. So there is this famous Hironaka's characteristic polygon, where instead of cutting out at height m3 minus 1/2, you cut at height m3 minus 1. Okay. So let's consider. So the problem here is precisely the fact that in the case of vector fields, you can have vertex with negative entries. Okay. So consider this example, and now I'm going to draw the polygon of this, the polyhedron source. Sorry. So okay. So this first term here gives the main vertex, which is at coordinate 0, 0, 3. Okay. And now there is this second monomial here, which is given 0, 0, 1, 2. Well, cannot select each one. And there is a y7. Perhaps there is a small mistake here. So this should be d over dy. Perhaps I'm going to correct this, but this is not very important. The important is this triangle which appears here in above, right? So, and then there is this coefficient here, which gives something which coordinates 1, -1, 3. Also, this is the point here. Now, let's compare the derived polygon that I've just defined with the characteristics polygon of Hironaka, which I denoted here by n2 prime. So if you cut out this polyhedron at height 2, at height let's say m3 minus 2, so it's at height 2, you just get one quadrant at with a point, a single vertex at coordinate 0, 1. Okay? But if you cut out at height 3 minus 1/2, then you capture this small. So this is the bottom drawing here. You capture this small side here, going from the point 1/2, 0 to the point 0, 1/2. And this is quite important because this is precisely the intersection of this this triangular face which appears here with that you capture by taking this intersection. So you'll see that if the intersection is too low, you don't capture this face, which is triangular face. And this is precisely the face that we are going to use in our algorithm. In some sense, if you don't capture this face by cutting out at a convenient height, in the next blow up, you are going to lose the information about the main vertex. Okay. And again, so this is precisely the problem, an example of the problems which are caused by the presence of vertices of negative coordinates. Yeah, so now the invariant. Okay, I'm going to explain the invariant. So the invariant, it's a little bit more complicated than in dimension 2. So the invariant of the foliation with respect to the coordinates x, y, and z, of course, because everything is computed with respect to the polygon, the polyhedron source, which on its turn depend on the coordinates. So now it's given by a vector of natural numbers, of 6 natural numbers. Okay, I'm going to explain which the meaning of each one of these entries. Okay, so M2 and M3 are the second and the third coordinates of the main vertex, right? Now, there is this delta, which is delta 1 and delta 2. I recall to you, just to go back a little bit. These, are the coordinates of the displacement vector. I mean, the vector which connects M to M prime. Again, they are rational because everything is rational, is defined over the rationals. I normalize it somewhere. Yeah, sorry. Okay, so there is this delta 1 and delta 2. And then there is this lambda, which is here just to normalize things and guarantee that this vector is an integer vector, is a vector of natural numbers. So I just multiply delta 1 and delta 2 by the factorial of M3 plus 1, because this is what guarantees that this will eliminate the possible denominators which appear in the expression of delta 1 and delta 2. Now, so there is this E, which counts the number of irreducible components of the divisor at the origin. So I recall to you that in our typical situation, there are either 1 or 2 components of the divisor. So E is either 1 or 2. And now the number which appears here is just E minus 1. So its range is it's either 0 or 1. So, okay, this is let's say, quite easy to explain. And now there is this important first component, which again is due to a phenomenon which does not appear in the case of, let's say, of classical polyhedrons, which is so-called the virtual height. So the virtual height is a natural number. I'm going to give an example in a moment, which is defined as follows. So it depends on the second coordinate of the main vertex. So if the main vertex is positioned at minus, let's say, start with this case, which is easier. So if the main vertex is has its second coordinate equals to 0, and the displacement vector is positive, or the displacement vector is positive, so the virtual height is just equal to M3. Okay? But there's a second case here. I'm going to illustrate an example where the main vertex is situated, let's say its second coordinate is equal to -1 and delta 1 equals to 0. And in this case, it's given by this expression, which I'm going to show to you what's the meaning of this. But so this is the integral part of M3 minus 1 plus 1 minus 1 over delta 2. Okay, so an example. Take this vector field here. And now, so its main vertex is at the point 0, -1, 4. Okay. And then the displacement vector is delta 1, delta 2, 0, 2/3. And now what's the virtual height? So now you see that there is this line here with this arrow, which links. In fact, this is the displacement vector is this vector which is represented with this arrow, this bold arrow here. Okay, and now what you do is that you extend the line given by this arrow, and now you see the point where it intersects the vertical axis given by v1 equals to v2 equals to 0. Right? So this is this point which appears here. And the formula for this point is just m3 minus 1 over delta 2, okay, which is it's 2.5, right? So 5 over 2. And the virtual height in this case is just the smallest integer number, which is strictly greater than this. Okay, so you take this possible rational number and you round out to the greatest integer number, which is to the smallest integer number, which is greater than this. So in this case, the invariant is given by this 6 numbers which appear here below. So I claim that now I'm going to explain to you what is the strategy of resolution of singularities. And I claim that if you compute this invariant with respect to a convenient system of coordinates, it will lexicographically decrease after each blowing up. Okay, provided that you compute it on nilpotent points, of course. So since it cannot decrease indefinitely by the lexicographical order, at some point you are going to get an elementary situation where all points are desingularized. Okay, so it seems a little bit complicated, but I'm going to explain why you need to. And so I'm going to explain to you the desingularization strategy, and then why we have to consider this fancy number which appears here, this h. Okay. Yeah. Okay, so we have all the ingredients to define the local desingularization strategy, but now I have to show to you how to choose the main phase. Okay, so you have this. I recall too that there is the m prime, which is the vertex of the derived polygon, situated at height m3 minus 1/2. And now we do exactly as we have done in the case of dimension 2. We define the main side. I'm not going to call this a main edge because it's not an edge of the polyhedron, but it's the edge. It's an edge of the derived polygon, and I call it the main side. Okay, so it's defined as follows. So if now I have drawn here the derived polygon n prime. So there are two situations. Either m1 prime is positive, and in this case I choose the face, the side, sorry, the side as being E0 in the picture. Okay, so in this case I choose E0. But if m1 prime is 0, then I choose E1. Okay, so the main side of n prime is either given by E0 or by E1. So it's E0 if the n prime is to the right of the vertical axis, and if n prime it's exactly let's say intersects the vertical axis, then you choose E1. Okay. Now make a drawing. So now you have the main edge. Yes, there is a small mistake here. So the main edge of the polyhedron n is the edge defined by the segment connecting the main vertex with the main derivative vertex. So the connecting M to M prime. This is the, you can see this in the drawing below. And then you have the main face of N prime, which is the unique face of the polyhedron, which intersects the derivative polygon on the main side that I have just defined, right? So you look at this leftmost drawing, have the main side given by this lowercase f. And then when you look at the face whose trace is given by small f, you have some face, capital F, which I'm going to call the main face of the polyhedron. Okay. Okay, so this is the main face. And as you can imagine, now the strategy consists in choosing a weighted blow-up whose weight is defined by a vector which is orthogonal to this main face. Okay, so there are two numbers which I'm going to introduce because they play a role in a moment. So you recall that there is this displacement vector delta, which is given by M prime minus M. So, and then the main side of the derivative polygon can be written as in this form. Okay. So, yeah. Okay. Sorry. Yeah. So, what I'm considering this is that the main side f is given by M prime plus a multiple plus let's say t times this vector c minus 1, 0, where t let's say varies in some interval of the real line, and then this number c lies on the extended the field of extended positive rational. So it can be a positive rational or eventually plus infinity. Okay, and I call this c minus 1, 0 the horizontal displacement vector. Well, okay, so I make just a drawing here to show to you what are the possibilities here. So you have M, recall you the main vertex, and then there is this delta minus 1, which is the, yes, delta minus 1, which is the, that should be that, is the vertical displacement vector. And then there's this C, which in some sense, it gives you the direction in inside the plane at height m3 minus 1. Okay, so these two vectors, delta minus 1 and c minus 1, 0, they generate the affine the affine plane which supports the main face. Okay, so I say that the main face is just given by m3 plus a convex combination of these vectors, the delta 1 minus 1 and c 0 minus 1. So you see that there are two cases where there are two extreme cases here. The case where c equals to 0 corresponds precisely to the case where the main side of the derivative polygon is vertical. Okay, and then there's the case where c equals to infinity. Is the case where the derivative polygon is a quadrant. Okay, so the case where you can have a quadrant in when you intersect. So you see this rightmost drawing here means that when you intersect your polyhedron with the plane at height m3 minus 1, you can get a quadrant, and in this case you have c equals to infinity in this expression. Well, okay. Yeah, so now, of course, the strategy of resolution of singularities in this case consists, as I said, in blowing up with the weight prescribed by this main face. Okay. So if you recall what you have done in dimension 2, it's quite easy to understand combinatorially what is the effect of blowing up with these weights. It simply corresponds to projecting the polyhedron by a shearing transformation in one of the three possible, let's say, three coordinate hyperplanes. So if you make the x directional blow up, let's say the uppermost here, you just project in the wall which lies on the screen, right? So you have this projection here, which I've drawn in the upper right part. Okay. If you make the y directional blow up, then you project the main face by a shearing transformation in the rightmost, in the plane, let's say in the plane given by second coordinate equals to 0. And if you make the z directional blow up, then you project in the bottom plane. Okay, so this is, of course, this is just a combinatorial effect of the blowing up, which means that when you make the blow up and don't make any other translations, you recall that the problem for us is that you have to keep track of these combinatorial transformations and then to the eventual translations, which are due to the fact that you have to recenter your coordinates on each point of the new exceptional divisor. Okay. But if you only consider the blow up, the combinatorial blow up without the translations, it's quite easy to see that in each one of these three possibilities, the invariant decreases strictly. Okay. So this is one of the ideas to why this invariant appears. Okay, so there's this z directional chart, which is quite easy to deal with, because when you recall that in our initial hypothesis, I said that the main vertex has coordinates 0, m2, and m3, where m2 is either equal to -1 or to 1, right? And then when you project on the bottom plane, which is what I've done here in the z direction, you easily see that you always finishes with an elementary situation. Okay. So by this I mean that in the vertical direction, when you look at the blowing up in the vertical direction, you always attain in a single step an elementary situation. Okay. So what the same phenomena appeared in the case of blowing up of planar vector fields. So this is one of the reasons, in some sense, why I can always guarantee that there are the number of irreducible components of the divisor in the typical situation is never equal to 3, because when you create a third component in the divisor, as it appears in the z directional blow up, then you already attained an elementary situation. Okay, so what we just have to take care is to the two transformations which appear on the rightmost side of my drawing here, eventually followed by of course by translations, right? So this is I recall, I just repeat that this is the combinatorial effect of the blowing up, but then there is a complicated issue, which is to guarantee that when you make the translations, there is no compensation phenomena, which could make your invariant does not decrease or even increase in this case. Okay, so I'm going to give an example to show why the main vertex, the height of the main vertex, cannot be the first invariant, the first entry in the invariant. So I recall to you that in the case of two-dimensional vector fields, there was a single invariant effect, that's quite easy, which was precisely the height of the main vertex. Recall this is something which always decreases by blowing up, but it cannot be so in this case, because okay, well, oh, there's something. Yeah, sorry. Yeah, so this is the example. So you consider this vector field here. Okay, it's drawing on the left hand side, and you compute the first 3 entries of its invariant. So the virtual height, in this case, is given by 2, because by definition, and then there is the position of this, let's say the second coordinate of the invariant, which is m2 minus plus 1. In this case, m2 equals to 0, so you have 1. And then m3, which is 2, okay, which is given by, m3 is given by this first, sorry. Yeah, m3 is given by, something wrong here. Sorry. I have something wrong in my example. I have to check out. So why? Oh, okay, no. So this Z3 d over dz gives the main vertex. Sorry, because you have to when you write this term in logarithmic coordinates, it gives you z square times z over d over dz.
Daniel,
Yes.
are you talking here about the main vertex or the higher vertex?
So in this case is the same thing, because this is a regular situation. Okay, so yes, this is if you take this polyhedron and you intersect with the plane given by v1 equals to 0, you just have a configuration where a regular configuration. Okay. I'm just checking out if so the vertex of coordinates 0, 0, 2 comes from z cube d over dz, and then there's this vertex 0, 1, 0, which comes from y square d over dy. Yes, and then there is x, this x z cube, which gives you this vertex of coordinates 1, minus 1, 3. And you see here that there is a negative second entry, precisely because when you write this expression in this polynomial in the logarithmic basis, you get a negative exponent in y. Okay, so in fact, in our invariant, we don't see this negative third vertex, because you just look at what happens in the plane v1 equals to 0. But when you make the blow up in the direction x, so this let's say this triangle here, given by this 3 vertex, is our main face according to what I've explained to you, right? So when you make the blow up with the weight given by let's say with the weight which defines the hyperplane which supports the main face, with the effect is to project this triangle here in the plane v1 equals to 0. But you see that when you project the vertex, this rightmost vertex with the coordinate 0, minus 1, 3 becomes, with coordinates 1, minus 1, 3 becomes 0, minus 1, 3. Okay, and then it becomes the main vertex of the transformed polyhedron. Sorry, yeah. But the original polyhedron had a main vertex with height 2, and now you have a main vertex of height 3, right? So the main height has increased precisely because there was something with negative coordinates which was lying in the main face. Okay, so there's a lot of small adjustments which are due to this kind of phenomena, and this justifies why you have to take this vector of 6 natural numbers. Each one of them, in some sense, takes care of one of these annoying phenomena which appears when you you consider these projections. So, so if you can check out what modulus some mistake of my part. So if when you blow up, you get this new vector field and the new invariant, as I defined. So the main height is 2, but then the second coordinate of the main vertex, which was in the beginning, it was 0. Now it's -1, right? It comes from here. So the invariant now is 2, 0, 3. And at the beginning, it was 2, 1, 2. So it's lexicographically smaller, even if its third entry has increased. Okay, well, yes, I'll explain this. Well, as in the case of dimension 2, in order to guarantee that the invariant decreases, you have to compute it with respect to a stable coordinate system. I'm going to explain this in more details next time because I think I don't have time, but the idea, if you recall what I have done in dimension 2, is that once we start with any coordinate system which is adapted to the divisor, we are going to be able to stabilize, in a sense that I'm going to explain to you next time, in order to get a new coordinate system. And moreover, this stabilization procedure is given always by a chain of coordinates which is of this triangular form, essentially. Okay, so this, in some sense, this is the essential part of the modular multiplication by a unit. I could say. This will be given by the preparation of coordinates will be given by a chain of coordinates where x tilde is equal to x and y tilde is y plus something which only depends on x, and z tilde is given by z plus something which depends eventually on x and y. So it's a triangular form. Yeah, what's written here? Yes. So in some sense, we don't want to have too much freedom in the choice of coordinates. Why? Because you see that all these invariants that I've defined, they are very, very, let's say they depend in a very strong way in the choice of coordinates. So in some sense, we don't want to have too much choice when fixing these coordinates where we compute the invariant. And in order to do this, I'm going to, in fact, one of the ways to do this is to rigidify the choice of coordinates by introducing an additional geometric structure, which I call an axis. I'm going to explain this. Okay. So I'm going to define to you what is what's an axis, but in some sense, it's something which guarantees that when you move from one admissible system of coordinates to the other, by admissible, I mean that it should respect the divisor and also respect this structure called an axis. And in this case, it should necessarily be given by something which is of this triangular form. Okay. So once you define, as I said, this axis, the local strategy of blowing up will be obtained by reading out let's say this combinatorial data based on the Newton polyhedron for an stable system of coordinates. Okay, so this is important. You recall that I said to you that when you compute the invariant that I have computed in the case of 2 dimensions, they were a sort of intrinsic object attached to the foliation, provided that they were computed with respect to a stable system of coordinates. And this case is the same thing. Okay, it means that when you compute this long invariant that I have explained to you with respect to a stable system of coordinates, it will be both intrinsically attached to the foliation, and moreover, it will be an upper semi-continuous function, by which I mean that you can, in fact, you can globalize this local strategy by always blowing up the locus of maximal where this invariant is maximal. So it gives you always a closed subset, a closed analytic subset of our ambient space. Yeah, so again, to make some parallels, this notion of stable coordinates is quite similar to the notion of well-prepared and very well-prepared coordinates of Hironaka's paper. Okay. In some sense, this again, this always, in some sense, a generalization of this Chinhausen transformation. But in Hironaka's paper, if I'm not mistaken, he asks for a more strong condition about the let's say which some sort of maximal contact situation. But I've explained to you that in the context of vector fields, you cannot expect in general to have the usual maximal contact situation, but you can still have some small sort of preparation, which Abiankars call the lazy Chinhausen. This some sort the lazy Chinhausen in our context is this stabilization of coordinates. Yeah. Okay. So I said to you that this preparation of coordinates it's much harder to understand in the case of vector fields, because when you look at this the D group given by these triangular changes of coordinates, it's quite easy to understand how it acts on germs of functions. But when you look at its action on germs of vector fields, it's much more tricky to understand the orbits of a vector field by the action of this group. Oh, I repeat the same things here. I'm sorry. I didn't have time to prepare too much this. Yeah, so I'm going to finish with this because I think it's enough today. So what's the nexus? The goal is, as I said, is we don't have, of course, we want to have some freedom in the choice of coordinates, but not too much freedom, because otherwise we are completely lost. I cannot extract good invariants from the good intrinsic invariants from the polyhedron, except if this polyhedron is in some sense has some rigidity. So in the case of two-dimensional vector fields, I recall to you that I've asked the coordinates to be always adapted to the divisor, in the sense that the divisor should always be given by x equals to 0. But in this case, in the case of 3 dimensions, this is not enough. So this is why I introduced this new structure here. So what's the nexus? So you start with your singular foliated manifold, MEF, this triple. And now, for me, an axis is a pair given by, so U is an open neighborhood of the nilpotent locus of the foliation. Okay, so I'm not interested in what happens outside the nilpotent locus. So I'm going to just to study what happens nearby the nilpotent locus. So I'm going, it will be enough for us to define this axis in some open neighborhood of the nilpotent locus. And now, on this neighborhood, I'm going to note by calligraphic A an analytic foliation by curves. So it is a new analytic foliation by curves, which in principle, of course, is different from F, which in some sense, it should be generically transverse to F. Okay, so what I mean by that, it means that, okay, it's adapted to the divisor. It's non-singular. It has no singularities. And if you place yourself in each point of the divisor, which is contained in the, let's say, in the divisor, which is contained in this open set U, where the axis exists, let's suppose that you fix some coordinates where the axis is given by D, is the foliation defined by D over dz. So the axis, it's the Z axis, in fact, the vertical axis. So the foliation is given by parallel lines, let's say lines parallel to the vertical axis z over dz. Okay. So in this case, the hypothesis is that the nilpotent locus is not contained, does not contain the axis through P. Okay, so you recall that this in our when I told you about this typical situation where I suppose that the intersection of the two divisors, like this, huh? I don't know if you see it, is not contained in the nilpotent locus. This is, in this case, I'm sort of generalizing this typical situation by saying that the leaf of the axis through the point P should not be contained in the nilpotent locus. Okay. So this is what first condition, and this holds for all points on the divisor. Okay. And then there's the points which are outside the divisor. And in this case, I ask for a more stronger condition, which is that the axis, the foliation A and the foliation F should not have a common leaf. Okay, so I can express this by this equation here. So if I choose local coordinates where the x is given by d over dz, I'm asking that this vertical axis given by x equals to y equals to 0 is not a leaf, a local leaf of the foliation f. Okay, this is the same thing as I see. The axis through P is not an invariant curve for f. Okay. So let's say the message here is that the axis is some new foliation, which is everywhere regular. Okay, and it's very transversal to the foliation which I want to desingularize. I made a drawing here. So you see that you have the nilpotent locus of M of F, and here you have this axis A, and you can imagine locally as being something like the Z, or let's say D over dz. Okay. So at no point you should have the nilpotent locus containing one of these axes. Yeah. So in fact, so an axis cannot exist if you had a nilpotent point which has had three components of the divisor, which lies in the intersection of three components of the divisor. Why? Because if you had three components of the divisor through a nilpotent point, of course, in this point here, any foliation which is tangent to the divisor should be singular. Right? So in particular, an axis, as I'm asking an axis to be invariant by the divisor, it should be singular here. So in this case, it would not be possible to have an axis. But as I said, this is a situation that we're always going to prevent, because each time that you create a third component in the divisor, the singularity which appears on this intersection of the three components will already be elementary. So no more interesting for us. But in the two first situations here, the two leftmost situations, you can have an axis. And in, let's say, in this middle situation, the condition that the axis is tangent to the foliation obliges that let's say the intersection of the two divisors should be the leaf of the axis through this point, right? So this is in this case, I'm asking that so the axis should be precisely the z-axis here, and in this case, we need that the nilpotent locus does not contain the z-axis. Yeah, okay. So just two last definitions. I think I'm going to finish in a moment. So we say that this triple MEF is controllable if there exists an axis as above. So in fact, this axis, in some sense, will be used as a tool to control, or more precisely, to rigidify the choice of coordinates. So at each step, we need to choose coordinates which will be stable this in a sense that I'm going to define next time, but in such a way that at the same time, on these coordinates, I'm requiring the axis to be given by this. Okay, so a coordinate will be adapted to the axis if in these coordinates, A is always locally generated by Z over dz. Okay, so one thing that you can see is that if you fix this condition on your system of local coordinates, it's immediate to see that when you change from one adapted system of coordinates to the other, sorry, I'm going to go a bit back, you redefine in the sense that this third component cannot depend, sorry, in the first two components cannot depend on Z. Okay, so in some sense, you already get this property of triangularity of your change of coordinates by imposing that it should always respect the axis. Okay, yeah. So we say that this singular foliation is controllable if you can find an axis, by which I mean a foliation, a regular foliation satisfy the condition that I showed you before. And in this case, this for upload here is called the controlled singular foliated manifold. So my last remark from today, yes, I'm going to finish with this, is that, well, as I said to you, it's not always possible to have a controllable singular foliated manifold, in particular when you start with a situation where you have an nilpotent point with E equals to 3, you cannot have, it cannot be controllable, right? Because in this case, there is no possible definition of axis at this point. But my last claim from today is that if you start with a situation where the divisor is empty, then it's controllable. Okay, so it's quite easy. You see here, but if you start with a situation where there is no divisor, then you can always define such axis. You can always define a sufficiently transverse regular foliation, which will satisfy our three conditions. Okay. Well, what's the idea of the proof? So it's very easy at the beginning, but now at the end we are going to use a quite powerful theorem. So since the divisor is empty, we have to choose just a regular one-dimensional foliation in the neighborhood of the nilpotent locus, which contains no invariant curve of f. Okay, so recall that this, when you are outside the divisor, we ask that the axis, the foliation given by the axis, has no leaf in common with the foliation given by f. Okay, well, how do we do this? Well, in fact, it's quite easy to do this locally in the neighborhood of each point by a very easy perturbation argument. Okay, so you place yourself on each point of the nilpotent locus, and what you do is that you give by a generic choice of coordinates, you can always define, let's say, one coordinate equals to constant, which is not, it's generically transverse to the foliation given by f. So it's quite easy to do this locally at each point, by, let's say, by chance, by choosing by randomly a change of coordinates. This will always be true to the axis given by one of the let's say two of the coordinates equals to constant. Now, by partitions of unity, you can glue together these local perturbations. Okay, well, I've detailed this argument in the paper. I'm not going to enter in detail, but it's quite easy to glue up these local perturbations. Let's say this local axis given on each point, and define a C infinity foliation, which I call A tilde, which satisfies all the requirements. Okay, this by partition of unity, it's quite, let's say, in the C infinity setting, you have a lot of freedom to do this. You can also do this by some sort of regularization and convolution method, but you end up with a C-infinity axis. And now now you are going to use the powerful theorem, which is the so-called Grauer's embedding theorem, which say that, well, it says that you can embed any analytic manifold in Rn for n sufficiently large. And one of the consequences that anything which is C-infinity defined on an analytic manifold can be arbitrarily well approximated by something which is analytic. Okay, so this is detailed in the Grauer's paper. So using this Grauer embedding, you can approach as well as you want this C-infinity axis by an analytic axis, which will satisfy all the requirements that I've listed. Okay, well, it's not very hard, but well, there's a very hard theorem behind. And indeed, when I adapted these results to the complex setting, we cannot use this argument because this Grauer embedding theorem is something which is very particular to real analytic manifolds. It's not true that an holomorphic manifold can be embedded in Cn for sufficiently high n. By it, I mean is not every complex manifold. This is time. Okay, so in our case, for if you want to adapt this construction to the case of vector fields over C, you have to change a little bit the definition of an axis. I'm not going to comment too much on this, but there is a notion of quasi-axis which allows us to define a global object without having to use the Grauer's embedding theory. So I think I'm going to finish here. Yes. So next time I'm going to explain to you how to use this axis to define what we call an adapted system of coordinates, and then to show how we can define an unstable system of coordinates, which will take care of this phenomena of full compensation, which could happen when you make the combinatorial blow up and then the translation. Okay. So I think I'm going to stop here. Thank you for your attention.
Thank you, Daniel. Stop the recording.